Hi and hello. This is High Physics YouTube channel. In this video, we are going to discuss dual nature of radiation and matter for grade 12. Dual nature of radiation and matter. We know that radiation is a wave, and we are going to attach the particle nature with the radiation, and similarly matter is made up of particles, and we are going to attach the wave nature with the matter particles. This is the entire essence of dual nature of radiation and matter. Now we are going to see the first part, dual nature of radiation, and in my subsequent video I am going to discuss the dual nature of matter. So dual nature of radiation, it all began in 1887 as scientists discovered that high frequency ultrasonic waves were used to emit certain negatively charged particles from the surface of the metal. We say it's a negatively charged particle because electron was not invented at that time. It was invented only in 1897 by J.J. Thomson. Before that, it was considered as a stream of negatively charged particles. So what they did, they allowed the ultrasonic or the high frequency radiation to fall on the metal surface. From the metal surface, negatively charged particles are ejected out. Stream of negatively charged particles. Later it was identified as stream of electrons. So this is the experiment done by different scientists like Hertz, Leonard and Halbach. In 1897, J.J. Thomson invented the electron. Now, we'll discuss a little bit about work function of a metal. We know that the metal is made up of free electrons. Free electrons are abundantly available in a metal. The free electrons are free to move inside the surface of the metal, but they cannot escape out of the metal. So what one should do to eject this electron out of the metal, to remove this electron out of the metal surface? So we have to supply energy to the electron so that it will escape the attractive forces of the ions that are available on the surface of the material. So this minimum energy needed for an electron or needed by an electron to escape from the metal surface is called the work function. Its unit is electron volt, EV. So it is energy, it is measured in electron volt, or we can convert it into joules. So minimum energy required by an electron to escape from the surface of the metal is called as the work function of the metal, and it is denoted by the symbol phi naught. A small numerical workout is given in the textbooks, which I have given here, right? So you can look into that leisurely. It's a matter of simple arithmetic. Now we have work functions are different for different materials. For example, cesium has a work function of 2.14. Sodium has a work function of 2.75. And aluminium has 4.28, copper has 4.65, platinum has 5.65. Everything is given in terms of electron volts. So work function differs from material to material. This energy, this minimum energy can be supplied, that is the work function energy can be supplied to the metal by any one of the physical processes. The physical process can be a thermionic emission, it can be a field emission, or it can be a photoelectric emission. Thermionic emission is when you heat a metal or when you supply a thermal energy to the metal, the electrons, the free electrons gain sufficient energy in order to overcome the work function, and they escape out of the material, liberated from the material. And this you call it as the thermionic emission. Similarly, in field emission, you provide the necessary energy to overcome the work function by supplying electrical field, positive and negative charges are supplied, or you place the material inside a plate or between a plate which is positively and negatively charged, so that they acquire the required energy to escape out of the material. This you call it as the field emission. The third type of emission is the photoelectric emission. Photoelectric emission, you supply the high frequency radiation to fall on the surface of the metal. As a result, the electrons, the free electrons at the surface of the metal, absorb energy from the radiation and attain the sufficient energy to escape from the material surface. This you call it as the photoelectric emission. So there are different processes by which we can supply this minimum energy so that the electron can escape the surface of the material. It all began with Heinrich Hertz in 1887, Leonard and Hallwag from 1886 to 1902. They observed this effect, which they call it as the photoelectric effect. Photoelectric effect means when you supply an incident radiation, then electrons are emitted, electrons are rejected from the surface of the material, and this electron is due to the photo or the light radiation or the electromagnetic radiation that falls on the surface of the material. So this effect, they called it as the photoelectric effect. They completely studied with experimental part by keeping, for example, the frequency of the incident radiation constant by changing the plate voltage. This is the plate voltage. Here you have a cathode, here you have an anode, and these cathode and anode are placed in an evacuated glass tube, and this is a window through which the electromagnetic radiation, high frequency electromagnetic radiation or the light rays can be passed, and that falls on the cathode. This cathode is made up of the material which we call it as the photoelectric material, as this material is going to emit electrons, photoelectrons. So this is a photosensitive or light sensitive material. So this window, you call it as the quartz window. This window was originally designed by Leonard, and this you call it as the Leonard window also. And you can change the potential of the plate A. You can increase the potential, you can decrease the potential, and you can even reverse the potential of the plate A or the anode by the potential divider arrangement, which is shown here, right? So all these people have studied the photoelectric effect experimentally by changing all the different parameters like intensity, frequency, the potential difference between these two plates, and they discovered and they experimentally calculated all the variations. But the drawback is they were not able to give theoretical explanations to this phenomena, photoelectric effect, because at this point of time wave theory of light or wave theory of electromagnetic radiation was more popular and it was well established. As a result, these people tried to explain these phenomena with the wave theory, but they couldn't give a satisfactory explanation for these changes. What are all the studies they have done? Heinrich Hertz, Leonard and Hallwag. That is what we are going to discuss next. They studied effect of intensity of light on the photocurrent. So you have this evacuated glass tube arrangement as we have discussed earlier. This is the photosensitive metal to which we are going to pass high frequency radiation, right? Electromagnetic radiation, or in fact light, high frequency light beam. Okay, and we are going to study the variation of intensity, light intensity. We are going to change the intensity of this light and the effect of this variation of light intensity on the photocurrent or the electrons emission, right? This is what their primary task. So they found that by changing the intensity of the current, intensity of the radiation, how the photocurrent varied, but they kept the frequency of the light radiation constant as well as the accelerating potential as constant. So they kept A at constant, A positive potential with respect to this cathode C, and also they kept the frequency of the incident radiation. They only changed the light intensity. So they found to be a linear line as shown in the figure. For a different intensity, photocurrent was directly proportional to the intensity. Right? So this is what they observed for high frequency radiation. Right? We should keep that in mind. And effect of potential. Second thing is effect of potential on photoelectric current. What they did, for a given frequency, the stopping potential is independent of the intensity. This is the result they have arrived at. For example, they kept the frequency constant, but changed the intensity, as well as they changed the potential between the plates C and A. Okay, so this is the second part. So first they kept the intensity at a particular frequency. If the frequency is fixed and the intensity is also fixed and the plate potential is fixed positive, right? Fixed positive, and they studied now. For the fixed potential, plate potential, the current was flowing, photocurrent was flowing from the cathode to the anode. Once they increased this positive potential, what happened? This current flow increased. As a result, more number of electrons are attracted from the cathode to the anode. So this is the graph which they show. As they increase the plate potential, positive plate potential, the current also increased. But at one point of time, it gets saturated. After that, even if they increased the intensity, the plate potential remained, even though they increased the plate potential, the current doesn't increase for the particular intensity and frequency, right? So this is the saturated potential. This is saturated potential and this is the saturated current. So now there is no further increase. Now what they did is they reduced the potential. They tried to increase the negative values of the plates, right? They reduced the potential of the positive potential of the A. So they reduced that, and as a result, what happened? The current decreased, because when the anode becomes more and more negative, what happens is that the electrons from the cathode are repelled. As a result, the current decreased. But still, the electrons that possess the highest or the maximum kinetic energy reaches the plate, and as a result, current doesn't stop to zero or doesn't reach zero, but there was a minimum current flowing through the circuit. And once they increase the negative values of the potential, that is, they increased they applied a higher negative potential to the plate A, what happened is that all the electrons are stopped. This means even the electrons with maximum kinetic energy is also stopped, and this you call it as the stopping potential. And this potential that is applied to the plate A, you call it as the stopping potential, right? Now they repeated this experiment with various intensity, but keep in mind they have fixed the frequency. They have not changed the frequency. Only they changed the intensity. Intensity of the incident radiation was changed. So they increased the intensity and plotted the graph. They increased the intensity and plotted the graph. So this was the graph they obtained. So as we said that we changed the intensity by keeping the frequency constant and found out that the stopping potential is the minimum potential that can be applied to the minimum negative potential that can be applied to the positive plate A, so that all the electrons are stopped. No electron reaches the plate A. This you call it as the stopping potential, as indicated here. We kept on increasing the intensity, but the pattern remains the same. And for all the intensities, the pattern is the same, and we have the same stopping potential provided the frequency is constant. So this is the startling discovery. So the stopping potential was same, minus V naught. This is the minimum potential, negative potential that is applied to the plate A, so that no electron reaches the plate A, or in other words we can say no photocurrent flows. This you call it as the retarding potential or the stopping potential as indicated A. So this is one thing. Second, effect of frequency on the incident radiation on the stopping potential. How the intensity is related to the stopping potential. This is what we are going to discuss this second. The energy of the emitted electrons depends on the frequency of the incident radiation. This was clearly evident from this graph. What they did is, this is y-axis, they have taken the photocurrent, and in the x-axis, as earlier, they have taken the electrode potential or the positive plate potential, right? Here, when the plate was given a highest value of the positive potential, and the saturation current was like this, right? Saturation current, no more, only a constant flow of current flowed from the cathode to the anode as the radiation falls on the photomaterial, that is the cathode C, right? Right. Now what happens at this juncture is that when we reduce the positive potential, what happens? The photocurrent also decreases. The photocurrent also decreases, right? The photocurrent also decreases, and when we apply negative potential to the plate A, what happens? It still further get reduced, and for a particular negative potential it becomes 0. This we call it as the stopping potential. This curve is for a particular frequency, say nu1, particular frequency of the radiation. Now what happens? They increase the frequency of the incident radiation, right? They increase the frequency of the incident radiation and found that the saturation current was similar, but the curve took a slightly different path, and as they decreased the positive potential, and they found out that the stopping potential was this one, V02 was the stopping potential. They required a greater stopping potential, a higher negative voltage to stop the photocurrent. And then they increased the frequency once again and found out that the stopping potential is also increases in the negative side. So greater the frequency, greater is the negative potential required to stop the electron, or the greater is the retarding potential required. So this is what given here. Stopping potential, more stopping potential means a stopping potential is more negative potentials, and if this is more, then higher the frequency of the radiation. We can put it in the vice versa also. Higher the frequency of the radiation, then you need a greater stopping potential. Greater the frequency of the radiation, then greater is the kinetic energy, so we need a greater retarding potential. What is the meaning is that if the frequency is more, then the kinetic energy of the electrons emitted from the photosensitive material cathode is higher, therefore we required a greater stopping potential. This is what the experiment says, right? Then frequency of the incident light versus stopping potential. This was the another study. So this is the stopping potential, and this is the stopping potential, and this is the frequency of the incident radiation. And what they found out is a straight line. So here, after this particular frequency, right? After a particular frequency, the graph between the frequency of incident radiation and the stopping potential was a linear curve. Higher the frequency, higher the stopping potential. That is what this curve indicates. But one startling information is that you need a minimum potential in order to initiate the incident emission of electron, right? So you need a minimum potential. That you call it as this, what do you call it as the cutoff frequency or the threshold frequency nu0. So this is what this graph indicates. So photo emission takes place only when you reach beyond a certain frequency. When the radiation is beyond a certain frequency called as the threshold frequency. When the frequency of the incident is higher than this threshold frequency or the cutoff frequency nu0, then only photo emission takes place. So this is one thing. This is the greatest invention, because they found out that you need a minimum frequency for a particular material. You need a minimum frequency. The incident radiation has to be greater than this minimum frequency, which we call it as the cutoff frequency or the threshold frequency, right? So all these experiments were done by all these people, but the problem lies in explaining this phenomena, theoretical explanation. So key points, what are all the points we have discussed so far? For a given material and constant frequency, photoelectric current is directly proportional to the intensity of the incident light. So for a given material and a particular frequency, photoelectric current is proportional to the intensity of the incident light, right? And similarly, for the given material and constant frequency, saturation current is also directly proportional to the incident intensity of the incident light. That is the directly proportional. As the intensity increases, saturation current also increases. As the intensity increases, the photoelectric current also increases for a particular material and constant frequency. And also one more finding is that for a given material, there exists a certain minimum cutoff frequency, nu naught, which we call it as the threshold frequency, below which no emission takes place, right? Below this frequency, no photoelectric emission takes place. Above this frequency, the photoelectric emission is directly proportional to the intensity of the incident light, which means above this frequency, if the intensity increases, emission also increases. And one more thing is that photoelectric emission is an instantaneous process. As soon as the light radiation falls on the cathode plate, the photoelectric emission takes place. So there is no time lag, right? So these are all the key points that have been observed through experiments by all these scientists, right? Now people tried to explain this photoelectric effect using wave theory of light, which was not possible. So that's why I have striked this. Photoelectric effect cannot be explained using wave theory of light. Let us see how. Free electrons at the surface of the metal absorb the energy from the radiation continuously. This is the classical viewpoint or the wave theory viewpoint, right? Free electrons at the surface of the metal will absorb the energy from the radiation, which is treated as the continuous flow of energy. We know that waves are having continuous flow of energy. So the electrons at the surface of the material or metal absorb the energy from the radiation continuously, which means greater intensity. If the intensity is greater, then greater is the absorption by the electron, which leads to greater kinetic energy of the emitted electrons. That is, the kinetic energy of the electrons is directly proportional to the intensity of the radiation, which is not true. Right? Okay. What we are going to say is kinetic energy of the electron is directly proportional to the frequency and not to the intensity of the radiation. Okay. And also over sufficient time, the electron at the surface. So for example, if the light radiation falls on the metal surface for a greater amount of time, then the all the electrons at the surface of the material will absorb this energy, and since it is for a greater amount of time, so greater energy they absorb and they overcome the work function and get emitted out of the metal, no matter what the frequency is, even for a very dull light, for a very small frequency of the light, which is also not true, right? We have seen that the photoelectric emission takes place only beyond a certain frequency called as threshold frequency or the cutoff frequency. So this is also not true. They were not able to explain using wave theory. One more thing is, since the entire wave front falls on the surface of the metal, all the electrons in the surface will take time to gain the required energy to cross the surface barrier. As a result, all the electrons are going to share the continuous energy, which means that the electron may take time to absorb this energy and come out of the material. As a result, there will be a time lag between the radiation incident on the material and with the photoelectric emission, right, or the electron emission. So there will be a time gap between them, but which is also not true. Photoelectric emission happens instantaneously. So wave theory completely failed to explain the photoelectric effect. This is the time point when Einstein came into the picture with his novel photoelectric equation. In 1905, Einstein published 3 papers, one on photoelectric effect, one on special theory of relativity, and the third one on Brownian motion. So this year is a special year, which we call it as the Annus Mirabilis, or the year of miracles. So Einstein produced 3 fundamental basic papers. Even though they are not related to each other, but in a way they are related to each other, and these 3 papers revolutionized the way the people saw physics, or it can be said like this: it has revolutionized the physics and took the physics into another realm, right? So Einstein's photoelectric equation is that he made a bold statement that energy of quantum radiation, he said radiation energy is not continuous. So first point, wave theory is shattered here. Radiation energy is not continuous. It is built up of discrete chunks of energy called quanta. So the incident radiation is made up of chunks of energy called quanta, and each quantum of radiation has an energy h nu, where h is the Planck's constant and nu is the frequency of the incident radiation, right? So nu is the frequency of the incident radiation multiplied by the Planck's constant. This is the energy of each chunk, right? And the second statement is, now an electron, a single electron at the surface of the metal absorbs a quantum of energy, one quantum of energy, h nu of radiation. So each electron absorbs one quantum of energy. If this quantum of energy is greater than the work function of the metal, then electron emission takes place. Then the electron is emitted with maximum kinetic energy. This is the statement. If this quantum of energy is greater than the work function 5 naught of the metal, then the electron is emitted with maximum kinetic energy. So he gave the equation: maximum kinetic energy of the electron is equal to h nu minus 5 naught. H nu is the incident energy of the radiation, nu is the frequency, h is the Planck's constant, and 5 naught is the work function. So if this energy is greater than 5 naught, then this equation you call it as the Einstein's photoelectric equation. So what the Einstein's photoelectric equation says, the maximum kinetic energy of the emitted electron is the difference between the energy of the incident radiation and the work function of the metal, right? So K max is equal to h nu minus 5 naught. So this is the Einstein's great equation, photoelectric equation, which won him a Nobel Prize in 1906. So if h nu is greater than 5 naught, that is the work function, right? Or if nu is greater than nu naught, then only the photoelectric emission will take place, where nu naught is the threshold frequency, minimum frequency above which only the photoelectric emission takes place. And this is given by nu naught is equal to 5 naught by h naught by h, Planck's constant. Otherwise we can state it in a different fashion: h nu naught is equal to 5 naught. So work function can be defined as h into nu naught, or nu naught is given by 5 naught divided by h. Work function divided by the Planck's constant is the threshold frequency. So this is the famous Einstein's photoelectric equation. In Einstein's explanation, how he explained Einstein's explanation, the process of emission is instantaneous. There was no time lag, right? Since each electron absorbs a quantum of energy, as the quantum of energy falls on an electron absorbs this energy, and if this quantum is greater than the work function of the material, then the emission takes place. This is instantaneous process, whatever may be the intensity. Even for a dull intense beam, if the energy of the incident radiation is h nu, and this h nu is greater than the work function, then instantaneous emission of electrons takes place. And Millikan actually wanted to disprove Einstein. So he meticulously did many experiments. He repeated this experiment by changing materials. So he chose different materials and performed this experiment, right? He varied the frequency of incident radiation with the stopping potential. You want to find the relation between the frequency of incident radiation and the stopping potential for different materials, right? And he plotted graphs, and in all the graphs he found that the ratio of this, right, or the slope of this line, or the ratio dy by dx is always a constant value, which is the Planck's constant. Actually, Millikan wanted to disprove Einstein, but instead what he did is that he proved Einstein. So this is the greatest proof for Einstein's photoelectric equation. Right? So this is the curve, the linear curve, that is the stopping potential is directly proportional to the frequency of the incident radiation. If the frequency of incident radiation is more, we need a greater stopping potential. Yes, agreed. But the photoelectric emission will take place only beyond a certain frequency called as the threshold frequency. And the slope of this curve, always gives a constant value, and this constant value is the Planck's constant h. So in this way Millikan proved that Einstein is right, and Einstein's quantum theory, that is, he treated the radiation, incident radiation, as a stream of particles each having a quantum of energy h nu. Right? So this is a breakthrough in quantum mechanics. Thank you.